Let's jump into writing code to describe memory arrays. But before we jump into writing HDL code, let's talk a little bit about key aspects whenever we design memory. So some of the key aspects is the depth, basically how many rows, and you are going to see me using addr_width to specify how many bits an address should be, and I'll make it as a parameter so our code is scalable, so you can actually specify the size of the memory as much as you want whenever you instantiate an instance of it. Also, the other key aspects is the depth, okay, or sorry, the width, and the data width is going to be another parameter that will describe basically how many bits is a word. It's basically the width of a word. Of course, we're going to have to specify the number of ports and the direction of the ports. So for example, in this here, you're going to see that I have 1, 2, and 3 ports. They're colored differently so that we can easily visualize it. 2 of these ports, which is the red and the green, are read ports, and the blue ports is actually a write port. So that's specified with the direction of the port. So synchronicity of a port access, whether you access it with a clock or at any time, this is not very clear on the graph, and as a designer you're going to have to make a decision when you should read or write synchronicity of a port. Generally speaking, a write is always synchronous. That's how I've seen it. The read is up to you whether you want it asynchronous or synchronous. Asynchronous meaning you can read it all the time. You don't have to wait for the clock to come over or the active edge of the clock, whether that's negative or positive. The other thing you're going to have to decide whenever you write code is simultaneous address access. Basically, if you're reading two at the same time, which is not a big deal, but whenever you're actually writing and reading to the same address, that might be a big deal, and you're going to have to talk about it. All right, so let's jump into coding. So let's start by describing a memory array that has 2 ports. One is going to be an asynchronous read, and the other one will be synchronous write. So I'll keep this open here on the side so we get to see it. And in Vivado I have opened a new file and I have already specified the input and output to save a little bit of time. So you can see here I have a couple parameters. The address width is 3. That tells me it's 2 to the power 3. I have 8 rows. And the data width is 8. That means it tells me each word in each row is 8 bits. And of course I need a clock. I need a write enable for the write. And of course I need one write address, one R address. Basically I'm describing everything you see in here. I need one R address for the reading address, one write address for the writing address. I need write data to write in, and I need read data to write output as an output. Basically that's what it is. So how do we describe this? Well, first of all, we need to specify the memory, and the way you actually specify the memory in Vivado is the following. You do logic, for example, and of course we need data underscore width, okay, -1 all the way to 0, okay, and we say let's call it memory. You can call it whatever you want. And here's the deal. So what you did is you just specified something that is, in this particular case, is going to be 8 bits, kind of like the W data or the reading data. But what I need is I need multiple rows. So the way we do it is by opening other brackets in here, and we're going to specify that I need it to go from row 0 all the way to row to the power address width -1. Remember, this address width -1 is a constant. So here, this particular expression is going to be evaluated before Vivado goes through the synthesis. So if we decided that address width is 3, it's going to be 2 to the power 3, which is 8. So 0 to the power 8 -1, which is 0 to 7. So convention says that we usually specify this to goes from, let's read it from left to right, data width -1 all the way to 0, because the least significant bit will be at location 0 for a word, and the most significant bit for a word is going to be data width -1. On the other hand, here what we usually define the memory is in quite the opposite. So we say from left to right, this is row 0, basically the top is row 0 and the bottom is going to be, in this particular case, is going to be 7. And in this way I defined a memory in Vivado, or in HDL, System Verilog. So now what we need to do is we need to figure out the write operation and the read operation. So let's start with the write operation. And well, we're going to decide according to the specs here, I need a synchronous write. So what I will do is I'll specify it as an always FF underscore or at positive edge of the clock, edge of clock. Okay, and I'll do begin and end, and here's how we do it. So we're going to see if write enable. Okay, what we're going to be doing is we're going to say memory, where do we want to write? Well, we want to write whatever the right address is. And what do you want to write? Well, you want to write whatever the right data is. And that's pretty much it. This is how you specify how to write to a specific location in memory. So you say, hey, go to memory, and the location is actually here. This is exactly how you do with arrays usually. This is the right address, and what do you want to write into it? The right data. Okay, if you want asynchronous read, basically a read that is available all the time regardless of the clock, so you're going to have to specify outside the always FF. So we're going to use a continuous assignment, and that basically tells me that the read data should be whatever is stored in memory at the read address. And that's pretty much it. This is how we specify a very simple RAM here. So if you go through, we're going to save that in here. We're going to go through the RTL analysis to see what did it interpreted it to be. So as you can see in here, you will see that it interpreted it as an RTL RAM. It takes the right address, the read address, both of them, read and write address, and the right data as an input and the R data as an output. Okay, pretty straightforward. Good. Okay, so now we move to a different model. So let's do 3 ports this time. So I'm going to add another asynchronous read and 1 synchronous write. So let's see in here. So I've opened a new file. I called it RAM 3 ports, and I specified the inputs and outputs. And you can see that basically I have 2 read addresses this time, the green and the red, as you can see in the figure. And I do have 1 write address, and of course I have 1 write data and a couple of read data. So what I did is I copied the code from the 2 ports because it's extremely similar. And what you're going to see is the following. So we have the write address is fine, the write operation is okay. However, the read operation is a little bit different. So I'm going to do the read operations in here. Okay, so what I have is I have a couple of ports. I have address 0, and I have basically data 0 and address 0. So if I need to add another port for read, all I have to do is just copy and paste that code, and that's pretty much it. So now we have 3-port RAM. Alright, so now what I want to do is I want to move one of these read data ports and make it synchronous as opposed to being asynchronous. And it's as easy as simple. For example, this one here, this should be 1 and this should be 1. I can move that particular one in here, and I'll basically, all I have to do is just put it within the always statement, and the always statement, as you probably know, is only activated when the active edge of the clock is happening. In this particular case is the positive edge. Of course, this is not a continuous assignment anymore, so I'm going to have to remove that assign in here, and because I'm using always underscore FF, I have to use non-blocking assignments. And that's as simple as that. So now if we go and we do, we'll save it, and we'll open the elaborate analysis here to get the schematic. We're going to see how different it will look from the previous versions. And you will see that the difference is mainly in the output. It's still RTL RAM, but what it did is it actually registered the port R data 1 and put it within a register. It's just passing it through a register, so it depends on a clock at this point. Now, what I want to do is I want to see where did it actually implement it or whatnot. So what we're going to do is I will run the implementation, and I want to see what type of resources did it actually use. Okay, so now that it has finished, you will see that I have used, in order for me to implement this particular 3-port, one is synchronous, one is asynchronous, we have used 16 lookup tables and 8 flip-flops to do this, and we did not use any of the BRAM. Okay, and that's interesting. Of course, if you need to have like a little bit more information, we're going to go to the implementation, and we can scroll down and we say the report utilization, and we'll open it, and you will see a lot more details here. So we're going to see the report utilization. Usually I take a look at, for example, we're going to save that. That's okay. We'll look at the summary in here, and it tells me, well, you use the lookup tables in here, and it's actually lookup params. It's specifically certain slices it used it. It's apparently very more efficient that way out of those available ones. Okay, and 8 flip-flops, and this is the number of inputs and outputs. That's all the number of bits. Okay, so now you can see in here that I did not use BRAM. So next what we want to do is we want to force Vivado to use the BRAM.